Somewhere in the darkness beyond our galaxy, a star is burning with a violence so extreme that it defies intuition. It is not merely larger than the Sun. It is not merely brighter than a billion ordinary stars combined. It is so immense that if you placed it where our Sun now sits, its surface would swallow the orbit of Jupiter, perhaps even Saturn, and still have room to spare. Its light would erase our skies. Its gravity would rewrite the architecture of the solar system. Its death would be an event so catastrophic that it could briefly outshine an entire galaxy. And yet, even that description may not be enough, because when we ask whether this is the largest star in the universe, we are not just asking about size. We are confronting the limits of physics itself. We are testing the equations that describe how matter holds itself together against gravity's relentless pull. We are probing the boundaries between what can exist and what must collapse. We are standing at the edge of what stars are allowed to be. The universe is vast beyond comprehension. There are hundreds of billions of galaxies, each containing hundreds of billions of stars. Most of them are modest, stable, predictable. But hidden among them are rare titans, stellar monsters so extreme that they challenge our understanding of how nature works. These are stars that live fast and die violently. Stars that burn through their nuclear fuel in mere millions of years, compared to the Sun's calm 10-billion-year lifetime. Stars that sculpt entire regions of space with their radiation and stellar winds. But how big can a star truly become? Is there a limit? Does gravity eventually lose the battle to radiation pressure? Can matter even remain stable beyond a certain mass? Or have we already found the ultimate giant? A star so massive that nothing larger can exist without tearing itself apart. Tonight, we travel across cosmic distances and backward through time. We will journey into star-forming nebulae where gravity assembles titans from collapsing clouds of gas. We will examine the physics that determines a star's size and luminosity. We will explore the rare hypergiants and supermassive stars that push nature to its limits. And we will confront the leading candidate for the largest star ever observed, a celestial behemoth that may represent the upper boundary of stellar possibility. Because somewhere in the silent dark, the largest star in the universe may already be burning, or it may have already exploded, leaving behind only the echo of its existence. And the answer to whether we have found it will force us to rethink what is truly possible in this universe. If you find yourself drawn to the quiet mysteries of the cosmos, subscribe to The Boring Universe. Like this video to support deep, long-form science storytelling, and leave a comment below telling us which part of the country you're watching from. Now, let us begin at the beginning, where stars are born. Before we can decide whether a particular star is the largest in the universe, we must first confront a deceptively simple question. What does largest actually mean? In everyday language, size implies diameter, the width of an object from one side to the other. But in astrophysics, size can mean several different things. A star can be the largest in terms of radius. It can be the most massive in terms of total matter. It can be the most luminous in terms of energy output. These are not interchangeable qualities. In fact, they often contradict one another. The Sun, for example, is a relatively ordinary star. Its diameter is about 139 million kilometers. Its mass is roughly 2 × 1030 kilograms. Its luminosity is defined as one solar luminosity, the benchmark by which we measure others. But the Sun is not particularly large, massive, or bright compared to the most extreme stars in our galaxy. Some stars are physically enormous in diameter yet surprisingly diffuse. Others are incredibly massive but compact. A red supergiant might stretch across billions of kilometers while having a lower surface temperature than the Sun. A blue supergiant might be smaller in radius but far more massive and thousands of times more luminous. This complexity arises because stars are not solid objects. They are spheres of plasma governed by a delicate balance between gravity and pressure. Gravity attempts to compress the star inward, pulling every atom toward the center. Opposing this is the outward pressure generated by nuclear fusion in the core, where hydrogen is fused into helium, releasing extraordinary amounts of energy. This equilibrium is known as hydrostatic balance. As long as fusion continues, the outward pressure prevents gravitational collapse. If fusion falters, gravity wins. The size of a star is therefore not determined solely by how much matter it contains. It is determined by the interplay between mass, temperature, radiation pressure, and the stage of stellar evolution. When we look for the largest star, we must distinguish between radius and mass. The most massive stars are typically blue, hot, and extremely luminous. Their masses can exceed 100 times that of the Sun, but despite their tremendous mass, they are not always the largest in radius. Conversely, red supergiants and hypergiants can achieve extraordinary radii, hundreds or even over 1,000 times the radius of the Sun, while not necessarily being the most massive stars known. A star like Ui Scuti, often cited in popular media as one of the largest known stars by radius, may extend roughly 1/700 times the radius of the Sun. If placed at the center of our solar system, it would engulf the orbits of Mercury, Venus, Earth, Mars, and possibly Jupiter. Yet Ui Scuti's mass is estimated to be around 20 to 40 solar masses. Immense, but not record-breaking in terms of mass. On the other hand, stars within dense clusters such as R136 in the Large Magellanic Cloud may have masses exceeding 200 solar masses, making them among the most massive stars ever observed. Yet their radii are far smaller than that of the most bloated red hypergiants. This reveals an essential truth: the largest star by radius is not necessarily the most massive, and the most massive star is not necessarily the one with the greatest diameter. To understand why, we must examine how stars evolve. All stars begin within molecular clouds, vast, cold regions of gas and dust. Under the influence of gravity, regions within these clouds collapse, forming protostars. As the cloud contracts, gravitational potential energy converts into heat. When the core temperature reaches approximately 10 million degrees Kelvin, hydrogen fusion ignites. At this point, a star enters what is known as the main sequence. This is the long, stable phase of stellar life where hydrogen fusion in the core provides steady outward pressure. The mass of the star at birth determines almost everything about its fate. Low-mass stars burn slowly and live for billions to trillions of years. High-mass stars burn furiously and exhaust their fuel in mere millions of years. Massive stars are hotter and more luminous because gravity compresses their cores more intensely, raising temperatures and accelerating fusion rates. This increased energy output produces stronger radiation pressure, which can partially counteract gravity in the outer layers. But here is where the path diverges. As massive stars exhaust hydrogen in their cores, fusion shifts to heavier elements. The core contracts while the outer layers expand dramatically. In certain stages, particularly for stars between roughly 10 and 40 solar masses, the outer envelope can balloon to extraordinary sizes, forming red supergiants. During this phase, the star's surface temperature drops, giving it a reddish appearance. Yet despite the cooler surface, the star's overall luminosity remains enormous due to its vast size. The key mechanism behind this expansion lies in the changing structure of the star's interior. When hydrogen fusion ceases in the core contracts and heats up, igniting hydrogen in a shell surrounding it. This shell burning deposits energy into the outer layers, causing them to expand and cool. The star becomes physically larger even as its surface temperature decreases. This is why the largest stars by radius are often red supergiants or hypergiants nearing the end of their lives. However, there is a theoretical limit to how massive a star can be. This limit is governed by the balance between gravitational attraction and radiation pressure, described by the Eddington luminosity. The Eddington limit represents the maximum luminosity a star can achieve before radiation pressure overcomes gravity in its outer layers. When a star approaches this limit, its intense radiation begins to drive powerful stellar winds, stripping away mass. The star effectively erodes itself. For extremely massive stars, radiation pressure becomes so strong that it prevents the accumulation of additional mass during formation. Even if a collapsing gas cloud attempts to form a larger star, radiation from the growing protostar can blow away in falling material. This suggests that nature imposes a ceiling on stellar mass. Observations indicate that this limit lies somewhere between 150 and 300 solar masses. Stars beyond this range would become unstable, shedding mass or collapsing rapidly. But radius does not have such a straightforward limit. As stars evolve into red hypergiants, their outer layers can expand to astonishing scales, even if their cores are relatively compact. The largest stars by radius are therefore often in a brief, unstable evolutionary stage. They are not stable giants that persist for long cosmic periods. They are swollen, dying stars on the brink of collapse. Measuring the radius of such distant stars is itself a complex task. Unlike nearby objects, we cannot resolve most stars as disks. They appear as points of light, even through powerful telescopes. Astronomers must rely on indirect methods analyzing luminosity, temperature, spectral lines, and distance estimates. Using the Stefan-Boltzmann law, which relates luminosity to surface area and temperature, astronomers can estimate a star's radius. If the luminosity and effective surface temperature are known, the radius can be derived mathematically. However, these measurements are subject to uncertainties. Distance estimates may be imprecise. Interstellar dust can obscure light. Stellar atmospheres can be turbulent and irregular, especially in hypergiants. As a result, when headlines declare that a particular star is the largest ever discovered, that statement often carries significant uncertainty margins. There is also the issue of definition. Stars do not have solid surfaces. Their outer layers gradually thin into space. Where exactly does a star end? The photosphere, where light escapes, is commonly used as a boundary, but for stars with extended atmospheres and massive stellar winds, this boundary can be diffuse. Therefore, declaring a single star as definitively the largest in the universe is more complicated than it first appears. We must also acknowledge the scale of the universe itself. The observable universe spans approximately 93 billion light-years in diameter. Within this vast expanse lie an estimated 2 trillion galaxies. Each galaxy contains billions to trillions of stars. Our current observations are limited to what we can detect. It is statistically probable that stars larger than any currently cataloged may exist beyond our observational reach. When we ask whether we have found the largest star in the universe, we are really asking whether we have found the largest star we can currently observe. And yet, even within our observable region, the search for stellar extremes reveals a profound truth about cosmic evolution. The earliest stars in the universe, known as population-of stars, may have been far more massive than most stars today. Formed from primordial hydrogen and helium, without heavier elements to cool collapsing gas clouds, these early stars may have reached hundreds of solar masses. Some theoretical models suggest they could have exceeded 300 solar masses. If such stars existed, they would have lived short, violent lives, ending in pair instability supernovae or direct collapse into black holes. None would survive to the present day. Their existence is inferred indirectly, through models of early cosmic chemistry and observations of ancient stellar remnants. This means that the largest star in the universe may not exist anymore. It may have burned out billions of years ago, leaving only heavy elements scattered across interstellar space. Thus, the question is not only about scale but about time. Stars are transient. Even the largest are ephemeral compared to the age of the universe. A star 200 times the mass of the Sun may live only 2 or 3 million years. In cosmic terms, this is the blink of an eye. When we look at massive star-forming regions today, such as the Tarantula Nebula in the Large Magellanic Cloud, we are witnessing environments capable of producing stellar giants. Within these clusters, gravitational interactions and dense gas concentrations can give birth to stars at the extreme upper limits of mass. In these environments, collisions between protostars may even merge smaller stars into larger ones, briefly exceeding theoretical formation limits. This possibility complicates the concept of a hard maximum mass. Under rare conditions, stellar mergers might create objects temporarily larger than what isolated star formation would allow. But even then, nature imposes constraints. Beyond certain masses, stars become unstable to pulsations, mass loss, and exotic processes such as pair production instability, where high-energy photons create electron-positron pairs, reducing radiation pressure and triggering partial collapse. These processes limit how large a star can grow and how long it can remain stable. Therefore, when we speak of the largest star in the universe, we are navigating a landscape shaped by gravity, thermodynamics, nuclear physics, radiation pressure, and cosmic history. We are not simply measuring diameter. We are interrogating the laws that govern matter under extreme conditions. To understand whether we have found the largest star in the universe, we must move deeper into the machinery of stellar physics. Not the poetic imagery of glowing spheres in the night sky, but the equations and forces that dictate what is allowed to exist. Because in the end, the size of a star is not determined by imagination. It is determined by pressure, gravity, temperature, and the fundamental constants of nature. Every star begins as a collapsing cloud of gas. Gravity pulls hydrogen and helium inward, compressing them into a denser and hotter configuration. As the cloud contracts, its core temperature rises. When the temperature reaches roughly 10 million degrees Kelvin, hydrogen nuclei begin to fuse into helium. Fusion releases energy according to Einstein's equation E equals mc squared. A small fraction of mass converts directly into energy, producing the outward radiation pressure that halts gravitational collapse. From that moment forward, a star exists in a delicate balance. Gravity pulls inward. Thermal pressure and radiation push outward. This equilibrium defines the star's structure. But as mass increases, this balance becomes more precarious. Low-mass stars are governed primarily by gas pressure. Their internal energy is dominated by particles moving at high speeds, colliding and resisting compression. But in massive stars, radiation pressure becomes increasingly significant. Photons themselves, produced in enormous numbers by rapid nuclear fusion, exert force as they scatter outward from the core. The more massive the star, the more intense the fusion reactions. The more intense the fusion, the greater the radiation pressure. And eventually radiation pressure becomes so strong that it begins to rival gravity itself. This is where we encounter one of the most important limits in astrophysics, the Eddington limit. The Eddington limit describes the maximum luminosity a star of a given mass can achieve before its radiation pressure overcomes gravitational attraction. If a star exceeds this threshold, the outward push of photons can drive material away from the surface. In extreme cases, the star begins shedding mass at extraordinary rates. Mathematically, the Eddington luminosity depends on the star's mass and the opacity of its outer layers. Opacity measures how effectively matter absorbs and scatters radiation. In stars composed primarily of hydrogen, electron scattering dominates. Photons collide with free electrons, transferring momentum outward. When radiation pressure equals gravitational pull, the star sits at the Eddington limit. If luminosity increases further, gravity loses its grip on the outer layers. For stars approaching 100 solar masses, radiation pressure becomes a dominant force in the stellar interior. Fusion proceeds at a furious pace. Temperatures soar to tens of millions of degrees. The core becomes convective, mixing material efficiently. The star grows intensely luminous, millions of times brighter than the sun. But this brilliance comes at a cost. As radiation pushes outward, it drives powerful stellar winds. These winds can carry away vast amounts of mass over time. Some of the most massive stars lose a significant fraction of their mass before they ever reach the end of their lives. This mass loss is not a minor detail. It is the reason why there may be a practical upper limit to stellar mass. Even if a protostellar cloud begins collapsing toward a mass of 300 or 400 suns, the forming star's radiation may expel surrounding gas before it can accrete further matter. Observational evidence suggests that stars rarely exceed about 150 to 200 solar masses at formation. In rare cases, particularly in dense star clusters, we have detected stars that appear to exceed 200 solar masses. But even these may have formed through mergers of smaller stars rather than through direct collapse. The cluster R136, located in the Tarantula Nebula within the Large Magellanic Cloud, contains some of the most massive stars ever identified. One of them, R136E1, has been estimated to possess an initial mass exceeding 250 solar masses, though its current mass may be somewhat lower due to intense mass loss. Yet even R136E1 is not the largest star by radius. Despite its extraordinary mass, its surface temperature is extremely high, over 50,000 Kelvin. High temperature means greater radiation output per unit area. According to the Stefan-Boltzmann law, luminosity scales with both surface area and the fourth power of temperature. A hot star does not need to be enormous in radius to shine brilliantly. In fact, the most massive stars are often relatively compact compared to red supergiants. Their intense gravity keeps them tightly bound, and their high temperatures produce blue or ultraviolet radiation. To find the largest stars by radius, we must look not at the most massive stars on the main sequence, but at evolved stars nearing the end of their lives. When a massive star exhausts hydrogen in its core, fusion halts there temporarily. Without outward pressure from hydrogen fusion, gravity causes the core to contract. As it contracts, it heats up. Hydrogen fusion continues in a shell around the core, while the core prepares to ignite helium fusion. The energy produced in these shell-burning layers exerts outward pressure on the outer envelope. The star expands dramatically. Its surface cools. It becomes a red supergiant, or in even more extreme cases, a red hypergiant. During this phase, a star's radius can increase by factors of hundreds or even thousands compared to its main sequence size. The core may be only a few million kilometers across, but the envelope can extend billions of kilometers into space. The outer layers become tenuous and unstable. Pulsations ripple through the atmosphere. Stellar winds intensify. The star may eject shells of material, forming nebulae around it. In this swollen state, the star achieves its maximum physical size by radius. But it is also at its most fragile. The reason for this fragility lies in the physics of fusion beyond helium. As the core contracts and heats further, helium fusion ignites, producing carbon and oxygen. Later stages may include fusion of carbon, neon, oxygen, and silicon. Each successive stage occurs at higher temperatures and proceeds more rapidly. Silicon fusion producing iron may last only days. Iron represents a dead end for fusion. Fusing iron consumes energy rather than releasing it. When an iron core forms and exceeds a critical mass, it can no longer support itself against gravity. Collapse becomes inevitable. For the most massive stars, another exotic instability can arise before iron collapse. At extremely high core temperatures, gamma-ray photons can spontaneously convert into electron-positron pairs. This process reduces radiation pressure because photon energy is converted into particle mass. With reduced radiation pressure, the core partially collapses, triggering explosive oxygen fusion. This phenomenon is known as pair instability. In stars within a specific mass range, roughly between under 40 and 260 solar masses, pair instability can cause a catastrophic thermonuclear explosion that completely disrupts the star. No black hole remains. The star is annihilated, dispersing heavy elements into space. This theoretical process places a further constraint on how massive a star can remain stable during its lifetime. Beyond certain thresholds, the universe simply does not permit long-lived stars of arbitrary size. Either radiation pressure strips them down or pair instability tears them apart. But what about radius? Could a star expand indefinitely during its red hypergiant phase? Here, too, physics imposes boundaries. As a star expands, its outer layers cool. Cooler gas exerts less pressure. The gravitational binding of the outer envelope weakens. If the envelope becomes too extended, it becomes susceptible to mass loss through stellar winds or episodic eruptions. Observations of luminous blue variables, such as Eta Carinae, reveal how unstable these massive stars can be. Eta Carinae underwent a giant eruption in the 19th century, briefly becoming one of the brightest stars in the sky. During this eruption, it expelled several solar masses of material. Eta Carinae's radius has fluctuated over time. It is not among the largest by radius, but it demonstrates how violent and unstable massive stars can become as they approach physical limits. Red hypergiants such as VY Canis Majoris or UI Scuti exhibit enormous radii, estimated at over 1,000 times that of the Sun. Yet these estimates are subject to uncertainties in distance and atmospheric modeling. Their outer atmospheres are irregular and extended, making precise boundaries difficult to define. Moreover, these stars are losing mass at prodigious rates. They cannot maintain their bloated envelopes indefinitely. The very processes that allow them to expand also ensure that they will not remain so large for long. In this way, the largest stars are also the most temporary. Their reign at extreme size may last only tens of thousands of years, a brief interval compared to the millions of years of their total lifetimes. There is another factor to consider: metallicity. In astrophysics, metals refer to elements heavier than helium. The first generation of stars formed in a universe composed almost entirely of hydrogen and helium. Without heavier elements to cool collapsing gas clouds, these early stars may have grown more massive than typical stars today. Lower metallicity reduces opacity, altering how radiation escapes from the star. In some models, lower metallicity environments allow stars to form with greater masses because radiation pressure is less effective at halting accretion. This suggests that the largest stars may have existed in the early universe when heavy elements were scarce. However, these primordial giants would have lived brief, violent lives. None would survive to the present epoch. Their existence must be inferred from simulations and indirect evidence. Thus, the search for the largest star is constrained not only by physics but by time and cosmic history. In the modern universe, enriched by heavy elements from previous generations of stars, formation conditions differ. Stellar winds are stronger in high metallicity environments because metals increase opacity. This enhances radiation-driven mass loss, limiting the maximum stable mass of stars today. When we combine all these factors, the Eddington limit pair instability, stellar winds, metallicity, and evolutionary expansion, we begin to see a pattern. Nature allows stars to become extraordinarily massive and extraordinarily large, but it does not allow unlimited growth. Each pathway toward greater size carries within it the seeds of instability. The most massive stars burn themselves down through radiation-driven winds. The most extended stars shed their envelopes through pulsations and eruptions. The most extreme cores trigger exotic instabilities that lead to catastrophic explosions. The universe appears to enforce a boundary. Yet within those boundaries, the extremes remain astonishing. A star 200 times the mass of the Sun contains enough material to form dozens of solar systems. A red hypergiant with a radius over 1,000 times that of the Sun would engulf most of our planetary neighborhood. A pair instability supernova can release more energy in seconds than the Sun will emit over its entire 10 billion-year lifetime. The largest stars represent the outer edge of what matter can assemble under gravity without immediately destroying itself. As we move forward, we will examine specific contenders for the title of largest known star. We will analyze how astronomers measure their radii and masses. We will confront the uncertainties in those measurements, and we will consider whether the true champion may not be a star we can see today, but one that existed in the distant past, because the question remains: within the laws of physics, within the observable universe, how close have we come to the absolute limit, and have we already seen it?